I guess we can start recording. All right, so I'm just gonna start off with like a little review from last week since it's been a while. A huge storm hit my town and we lost power for like a while, so that's why I wasn't here. But last class we talked a few weeks ago we talked about bonding, naming, compounds, atoms, molecules, and ions. Before that we talked about these Lewis dot diagrams, and these were the diagrams for these respective elements. So basically review on ions. Ions are basically just like charged atoms. Like an atom with a positive or negative charge is called an ion. Only electrons participate in like transferring or being shared or taken. Positively charged ions are called cations. Negatively charged ions are called anions. Monatomic means a singular atom or like one atom. Polyatomic means more than one atom. It means many atoms. And the octet rule is basically where most atoms need 8 valence electrons to get a full octet, a full outer shell. That's 8. They only gain, lose, and share electrons, never protons. Quick review on this too. Ionic bonds are between metals and nonmetals. The metals they form cations and nonmetals form anions. So basically an electron goes from the metal to the nonmetal. So then the metal becomes positive and the nonmetal becomes negative, and they bond because they're ions, and then the positive and negatives attract. For example, NaCl. Na gives Cl an electron, so it becomes Na plus and Cl minus. And because there's that positive and negative attraction, it becomes NaCl. Here's the Lewis dot diagram for NaCl's interaction. Here's some practice with it. And for naming, all you have to do is add I to the end of it. So for example, sodium chloride or magnesium phosphate, you would add ATE if it's a polyatomic ion. So here we see that, well, it's PO4, 2. PO4 is consisted of like phosphorus and oxygen, so that's polyatomic because it's more than one. But here it's just Cl, and that's just chloride, and that's just one, so it's just ID. Here's some more practice. Covalent bonding. It's basically just between two nonmetals, and the atoms share the electrons instead of like transfer them. This is for naming covalent compounds. You just like add one of these prefixes onto the beginning of one. For example, disilicon hexabromide, you add IDE to the end of the second element, or like carbon tetrafluoride, and you never add mono in front of like the first element. So NO would be like nitrogen monoxide, N2O would be dinitrate monoxide, and so on. Polyatomic ions, again, poly just means many. So polyatomic ions are just ions composed of like multiple atoms. Here's the little list of like polyatomic ions that I asked you guys to like know and practice with. Hopefully, if you guys did the homework, you guys would be pretty familiar with some of these. These were the review / key points from last lesson. Cations are positive, anions are negative. Monatomic means a singular atom. Polyatomic means more than one atom. Ionic bonding is between a metal and a nonmetal. Ionic naming, you just add I or 8. For covalent bonding, it's between two nonmetals, and for covalent naming, you just use the numeral prefixes and then add IDE at the end. So that was the homework. This was the contact information. All right, so now let's just move on to today's lesson. Any questions? Nope. Okay. So these are the units we're going to be learning today. We're just going to go through balancing equations and then moles and stoichiometry. By the way, if you guys don't have your calculators out now, I would suggest that you guys go get them. If you to find your calculators. A pen and pencil might be helpful as well, but a calculator is a big thing for this unit. Well, for moles and stoichiometry. I'll give you guys a minute to go get them. Okay, I'm assuming you guys have calculators now. For now, we're just going to talk about balancing equations and like molar. Actually, no. In a basic chemical reaction, atoms and their masses are always conserved. This means that there should always be the same number of atoms on each side of the equation. So, I don't know if you guys have heard of like the conservation of matter, but in chemistry, it means that atoms can't be created nor destroyed in a chemical reaction, only rearranged. Like how matter can't be destroyed nor created, but only like made into a different form. Okay, so that works within chemistry as well, where atoms have to be the same on each side. So a balance equation is an equation in which the number of atoms of each element as a reactant is equal to the number of atoms on the element as a product. So a reactant is like the things that react, they're on the left side of the arrow. And a product is like what you get from the reaction, it's on the right side of the arrow. For example, if hydrogen combines with oxygen to make water, is this equation balanced? H2O, I mean H2 plus O2 equals H2O. You guys can type it in the chat. Tell me if you think it's balanced or not, and why or why not. Okay. Never mind. What? So, no, it is not balanced because you can see that there's 2 hydrogens on this side, 2 oxygens on this side. That's good. There's 2 hydrogens on this side. That's good. But there's only 1 oxygen here. So if you want to count them, you see that there's 2 on this side, 2 hydrogens, and 2 oxygens. On the right side, there's 2 hydrogens and only 1 oxygen. So it's not balanced because there are not the same number of atoms on each side. So hydrogen is fine because it's 2 and 2, but oxygen is 2 and 1, so you need another oxygen here. But the way to balance chemical equations is to place coefficients in front of the reactants or products. You may only change the coefficient in front of the compound. You can't change the subscript. So you can't add a 2 down here. Oh, if you guys can see this little laser thing, you can't add a 2 there. You have to add it in front of the whole compound. So something like that. But you would have to add it in front of the whole compound, not just the single element. So this is what it looks like correctly. 2H2 plus O2 equals 2H2O. If you count the number of H's and O's on each side, there's 1, 2, 3, 4 H's, and 1, 2, 2 O's. So 4 H's and 2 O's. Over here, there's 1, 2, 3, 4 H's, and 1, 2 O's. So the coefficient counts for like the whole compound. Okay. So basically the steps to do this are you would list the elements, count the atoms of each element on each side, determine the coefficients that will create the equal numbers of each element on each side, check it, and then the process of like balancing equations is a trial and error process sometimes. So it's best to use a pencil. And the more you practice, the better you'll become with seeing these patterns. And then you can maybe do it with pen, but like, uh, here's some helpful rules. The 2-3 rule. If the count for an element is on 2 for one side and 3 on the other side, you'll probably need to make the total 6. So that means like, uh, if there's 2 O's on one side and 3 O's on the other side, 6 would be like the lowest common denominator. So you would have to multiply it by 2 and by 3. Well, I'll explain later. You guys will see. You guys would save single elements for last because those are the easiest to change. If there's a polyatomic ion that is the same on both sides, just keep it together. Don't like break it apart. And then if hydroxide is only on one side, it may be helpful to write water as HOH instead of H2O because it's basically the same thing. 2 hydrogens and 1 oxygen. And then be careful when counting an element, especially if it appears twice on one side. So if you look at this example, first you would list the elements, so Cl, Na, and Br, right? Then you would count the elements. There's 2 Cl's on the left side, 1 Na, and 1 Br. On the right side, there's 1 Cl, 1 Na, and 2 Br, as you can see. So in order to do this, to even it out, you would add a 2 there. So then these would become 2 because 2 NAs and 2 CLs. So that works out. And then on the left side, you'd have to balance that out too. So you'd add a 2 there, and then that would happen because then there's 2 NAs and 2 BRs. So then the whole ratio is 2, 2 to 2, 2 to 2, and 2 to 2. Therefore, it's balanced because there's 2 of each element on each side. No, it's balanced. For if you take this as an example, list the elements Mg, Al, and Cl, count them. You guys can count them yourself. How many magnesiums are there? How many Als are there? Remember, the subscript only counts for this element, not the whole thing. So there's only 1 Al, and then there's 3 Cls. There's 1 Mg here, 1 Al here, and 2 Cls here. So here, you can kind of use the 2-3 rule because there's 3 here and 2 here. So all you have to do is add a 2 on this side and a 3 on this side to make it even. So 2 and 3, you see, because first there was 3 on the left and 2 on the right. Then you just flip it around and add 2 on the left and 3 on the right. And now it's even because 3 times 2 makes 6 and 2 times 3 makes 6. So then that would make 6 CLs here, 3 Mgs, 6 Cl here, and 2 Al. So now we just have to balance out the Al and Mg. So you would add a 3 in front of the Mg to make that 3, and a 2 in front of the Al to make that 2, because we're doing the single elements last. So you go from here to here, where there's 3 here, so then, and 2 here. So this changes to 2, and this changes to 3. Now you check if they're even. There's 3 Mgs here and 3 Mgs here, that's good. 2 Als here, 2 Als here, that's good. 6 Cls here, and 6 Cls here. So that's all good. And this would be the final balance equation. So now it's balanced. This one, it looks confusing, but it's really not. You see these polyatomic ions, when you count them, you just keep them together, like SO4, OH. You list the elements or the compound, the polyatomic ion. You would see iron, Fe, SO4, sulfate, Ca, calcium, and OH hydroxide. Once you list these polyatomic ions and these elements, then you would count them. So just take your time and count. How many Fe's are there? There's 2. How many SO4s are there? There's 3. Ca, 1. OH, 2. I trust that you guys can count the rest. How many Fe's are on the right? 1. SO4 right here. There's 1. Ca, there's 1. And OH, there's 3. So in order to balance them, you see there's a 2 and a 3 here, so you use a 2-3 rule. Add a 3 on the right and the 2 on the left. Or you would do the 2 first by itself. Yeah, so then there's 2 Fe's, and now the Fe is even. And there's 6 hydroxides on the right side. Then you would add the 3 there, so then there's 3 Cas and 6 OH. So you see that 2-3 rule plays in action because there was a 2 here and a 3 here. Then you just add a 2 on the right and a 3 on the left. So now it just makes 6. And 6 and 6 is even. Now you just balance out the rest of them. You take the Ca and the SO4 on the right and you multiply them by 3 because they both need 3 and it's conveniently one compound. So you put a 3 there, and then these two both change into 3's. So now it's balanced because 2 and 2, 3 and 3, 3 and 3, 6 and 6. See, so there's an even number of atoms and ions on each side. You can do this example as well. Notice that OH doesn't appear on both sides. It only appears on the left. But if water is on the other side, you can write it as HOH, because OH becomes H2O basically. It'll be easier to balance that way, so try balancing this equation. Whoops. If you have a paper at home, you can go ahead and do it yourself. I'll give you guys a minute. Remember the first step, you just list the elements and list the compounds. Second step, you just count them. Third step, you just find the ratios to make it right. And then the fourth step, you just check it again to make sure it's all even. And it should work out for you guys. So I'll give you guys a minute or two to do that. Okay, so I'm just gonna assume that you guys are all done. If you're not, just tell me in the chat and I'll give you guys another minute, but it should have been enough time. This is the final answer, the balance equation. 2 FeOH3, 3 H2SO4, Fe2SO4, 3, and 6 HOH, basically 6 H2O. Now we can try this one. Notice how oxygen appears twice on the product side because there's CO2 and H2O. So when you count, you just count both of them. Well, try balancing this equation. I'll give you guys like a minute or like 30 seconds to do this. It's not as complex, but you can see there's a big 12 behind the H in the beginning. So go ahead and try and figure this one out. List the elements, write down the numbers, you just count them, and then make the numbers even, and then check it and make sure you're right. By the way, this isn't the part that you would need your calculator. That comes in after this. All right, so hopefully you guys are done with this one. The answer is C5H12 plus 8O2 equals 5CO2 plus 6H2O. So when you check this, you can see that there's 16 oxygens on this side, 12 hydrogens, and 5 carbons. Here, there's 5 carbons, 10 oxygens, plus another 6 oxygens, so that's 16, that matches. And then 12 hydrogens, that matches. 5 carbons, that matches. And therefore, it's balanced. Now we're going to talk about moles. Um, these are the units for this unit. Um, you need to know grams. It's grams. Um, there's not much to say about that. For molar mass, though, it should be on the periodic table. So, for example, the molar mass of nitrogen is just 14 because it just says it right here. Molar mass of oxygen is just 16. It says it right here. You can just round up to like 2 digits, 2 sig figs. But if there's more than one element shown, just add the masses together. If there's a subscript, multiply the element's mass by its subscript. For example, O is just 16 because that's what it says here. O2 is 32 because there's a subscript, so you do 16 times 2, and that's how you get 32. NO is 30 because nitrogen is 14, oxygen is 16. 14 plus 16 is 30. NO2, so here you would do O2 first, which is 16 times 2, and then N is just 14, and then you add that up. So 14 plus 16 times 2 would be 32 plus 14 is 46 grams, or grams per mole. Yeah, let me change that real quick so you guys don't get messed up. It's supposed to be grams per mole. Okay. Um, and the unit for moles is mole. I like how they shorten that down for us. Particles, PTCLS. It doesn't really matter. It's just particles. So yeah, these are the basic units we will be using from here on. Now would be a good time to have your calculators out. So just for practice, you guys can go ahead and find the molar masses for S, PO4, BRO, H2O, and NF3. If you want, you could also just like name these compounds and elements if you want. I'll give you guys a minute to do this. It should be on the periodic table. Just have your periodic table out. If you don't have one, just look it up online. Don't look up the molar masses for it. Just look up a periodic table and try and find all the masses for it, and just like add them up if you need to, or just like have that there. Write your answers down on a sheet of paper, and I'll give you guys the answers. Alright, so I didn't animate it to give it one by one, I just made it all at once. So if you have your answers, you can check it now. If you need another minute, I tell me in the chat, otherwise I will reveal the answers. Also, I didn't see that chat a while ago. Yeah, you're right, it was not balanced, but thank you for that, I'm sorry. Anyways, these are the answers for the molar masses. Sulfur is 32 grams per mole. Phosphate is 95 grams per mole. BRO is 96 grams per mole. Water is 18 grams per mole. And NF3 is 71 grams per mole. So that's that. Now we're just going to look at this chart. This is mole conversions. So this is converting grams to moles and moles to grams. Same with like particles and liters of gas. But for now, we're not really going to look at the bottom because we don't need that. But basically this is how you use it. It looks confusing, but it's really not. 7 grams of nitrogen, for example, if you had that, you would just divide it by the molar mass in the periodic table. So you would take 7 grams divided by 14 because that's nitrogen's molar mass, and then you'd get 0.5 moles of nitrogen. Yeah, basically moles is just grams divided by molar mass. And we've just practiced doing molar mass, so that shouldn't be a problem. For example, here you guys can do calcium. With 10 grams of calcium, how many moles would there be? So basically you just take the 10, you divide it by the molar mass, which is 40 for calcium. So 10 divided by 40 equals 0.25 moles of calcium. Now, hopefully that makes sense to you guys. Now we can look at a bit further. How many moles of nitrogen are there in 3.5 grams, and how many particles are there? So I know we didn't talk about this a second ago, but to find particles, you would just multiply by Avogadro's number, which is 6.022 times 10 to the 23rd power. And to find particles to moles, you just divide by 6.022 times 10 to the 23rd power. But it's really simple. Like if you have like 0.5 moles, you just do 0.5 times this number, and that's the number of particles. I know it's going to be a huge number, but like particles are small, so like it kind of makes sense. So in 3.5 grams of nitrogen, you would do 3.5 divided by 14 because that's nitrogen's molar mass. So 3.5 over 14 times 6.022 times 10 to the 23rd to find the number of particles. So first you get 0.25 moles from doing 3.5 divided by 14, which is grams over the molar mass, right? So that's 0.25. That's how many moles there are. So you answer the first question. The second question, to answer that, you just multiply by 6.022 times 10 to the 23rd power, and you would get 1.5055 times 10 to the 23rd. And we got to use sig figs because we didn't practice that for nothing. 0.25. Wait, does that have 2 or 3? Either way, the answer would be 1.5 times 10 to the 23rd nitrogen particles. So that's how many particles there are, and that's how many moles there are. Now we can do the same thing with calcium. But instead of finding moles, we're going to find grams. So here we give you the moles. It says there's 0.75 moles of calcium. So how many grams are there? 0.75 times 40, because 40 is calcium's molar mass, right? So you do 0.75 times the molar mass, which is 40, and you would get 30 grams of calcium. So that's how many grams are. And then to find the amount of particles, you just do moles times Avogadro's number. So we're to give you the amount of moles of calcium. It's 0.75. So then you multiply it by 6.022 times 10 to the 23rd power equals 4.516 times 10 to the 23rd power calcium particles. Round that down to 4.5 times 10 to the 23rd calcium particles, and that is your final answer. I think that's it for today. Here's some homework. The top one is, it's just a link. On that website, there's like a ton of worksheets just to like, for balancing and stuff, for balancing equations. I think it'd be very helpful if you guys did a few. And then the second link is for mole conversions / stoichiometry. It gives you questions, answers, and stuff about like molar mass, amount of moles, amount of grams, I think some particles. But yeah, that should be it. If you have any questions, here's my contact information. Don't hesitate to ask me. And thank you so much for enrolling and joining today's lesson. I hope you guys can all make it to the next one. Thank you so much.